me? Is this any better? Yeah. I'll keep the glasses off because there's too many moving parts here. So, okay, let's try this. Part 2, okay. What happened to the pointer? Here you go, yeah. Okay, so what we said we do in the second part is actually an overview of more recent areas in active materials. So this is not going to go into any particular depth, and we're running a little late, but we hope to get through all of it. So the idea is that what I've shown you here is cool. So far, this is just the introduction, but in some ways, just active Brownian particles. They're quite close to equilibrium, and they can be a little boring. So let's try to be more general in what active matter can do. So the first thing I wanted to talk about, and that's strictly a couple of theory slides, is what's now one of the focuses of the field, which is active solids. So we've seen a bit of an active solid already in the active glass that we just saw earlier. And so the idea is that I can say something more generic. So let me go back to linear elasticity. And so linear elasticity, I tend to write my stress tensor as some giant matrix of stiffness coefficients, K, I, J, K, L, epsilon, K, L, where epsilon, K, L is the strain tensor or the symmetrized gradients of the displacement field. Now, if you do this for nice isotropic solids, so let's say your stereotypical piece of like just rubber, yeah, you can write in 2 dimensions. You will be able to write this, or even in higher, as a bulk modulus on the trace of the strain tensor, and the shear modulus for the traceless parts of the strain tensor. This is very generic. So what I want to say is, what happens to all of this if you make it active, and how you can make it active, and how this gets modified. So the equivalent of the overdamped Langevin equation, which I just wrote down earlier, for in continuum for one of these systems, would be, instead of writing zeta Ri dot is equal to sum of the forces, yes, overdamped, I write zeta time derivative of displacement field is equal to F. So this is an overdamped Newton equation here, again, for continuum. And I'm going to write this now as the divergence of a stress tensor, so as dj sigma ij, okay? And what I wanted to say is, if I make things, this is a passive overdamped equilibrium systems. If I make things active, they can be active in 3 different ways inside a solid. So the first way, and I should have actually labeled, okay, let me actually do it yeah. The first way is that I could mess around with my coefficients here, K, J, K, L. And in fact, this is work which has been done by Vincenzo Vitelli and the people around him, who says that, well, equilibrium actually constrains these by symmetry, but if I allow for active terms, and I'll show you an example in a moment, I can get extra pieces in my stress tensor which are illegal for a system which is in thermal equilibrium. So I can get extra what's called odd elastic pieces in my coefficient matrix. The second way I can make these things active is actually much simpler, and it's the same way as we've talked about when we did active Brownian particles. Is I could say, okay, I write dTu is divergence of a stress, for example, from the passive potential of the harmonic repulsion that we had. But I could have explicit active forces in here which don't derive from a potential, which are not part of a stress tensor. For example, here, active Brownian driving, Fi act, just free active forces coming, say, from the crawling of a substrate. So we've seen these guys already, and I'll show you an example of what this does in the solid in a moment. Then finally, I could also just say, okay, my stress tensor, in fact, here, far from being exotic like this, it could have a passive piece, and they could have an actually reasonably well-behaved active piece in it explicitly. And that's very relevant, for example, in cell sheets where things are pulling on each other, okay? Yeah? Yeah, this is there's an implicit. Yeah. It's more complicated. You technically still have force balance, else I couldn't write down a stress tensor, but there is funny things going on with the torques, and in fact, I think best is if I show you this slide, where explaining where this comes from, yeah? So I don't want to go through this, it's also not my work. So the idea is that I can have active forces which are odd. And for example, a microscopic example would be, instead of having just springs, which are if you pull and push, is springs where if you pull them, they make a couple up and down, so they make counter rotations. If I push them, they also make counter rotations, but in the opposite direction. So this is not identical, but strongly related to the idea of non-reciprocal forces. So that I can get things which go in directions different from the expected ones coming from a potential. Then you can do the whole calculation. You can also derive this more generically, that you allow to have asymmetric pieces in your stiffness matrix. So for example, that a couple of compression to a rotation, like you can see it here specifically, or shear to a twist, okay? And so you can get extra coefficients here, for example, the K0 in here. And because of this, I can make cycles of compression and expansion in these systems, integrate the force times displacement field. And so from that, I can eventually show that the amount of work I can do in these systems over a cycle is non-zero. So I can use this to make engines. So this is not the only way to make an engine. I'll show you another one in a moment. But this is one way of making, say, an active engine inside an active solid. The one I wanted to spend a bit of time on, I'm conscious of being actually slow in here already, is coming back to this idea of active Brownian driving and in fact velocity correlation functions, yes. And so the idea here, and there were questions around this, let me be more specific. Let's take these active Brownian solids. So here is a picture of the disordered N field, so the disordered field of the activity itself. I want to show that having this plus an elastic solid in fact gives you these kind of long-range velocity correlations which were just mentioned. So the idea is, let's be a bit more specific, if you're in a glass, say you're stuck in an energy minimum and you're not relaxing particularly fast, so your alpha relaxation time scale is large compared to the persistence time of the activity, then I can approximate everything by expanding around one minimum of my potential energy landscape, and I can write my dynamics as fluctuations of the velocity being active driving, and this is the expansion of the potential into the Hessian matrix here, Kij. Then you can solve this one formally, and you can already show that this is explicitly out of equilibrium because you break equipartition. The energy per normal mode of this, where this is the modes of this matrix here, have not a constant, so you see the zeta V0 squared tau over 4 in front. This would be the active effective temperature which I introduced earlier, but you get a piece which depends on the eigenmode itself. So that breaks the equipartition. That says explicitly different modes have different energy. So this is one way, again, smoking gun for activity. This has some very interesting consequence, because what you can do is you can do a continuum argument on this. You can write down a continuum version of overdamped dynamics here in real space with dynamical matrix and active driving. Displacement field again. In Fourier space, this diagonalizes with an active driving in here, which acts then as a colored active noise, because this thing has a time correlation function, as we just derived earlier. In Fourier space, in frequency space, this has a Lorentzian spectrum, so tau omega squared down here at the bottom. And because of this Lorentzian spectrum, this is going to change how these modes, which would normally be diffusive and damped, act with each other. So you can compute this exactly. You can decompose this matrix into longitudinal and the shear part with bulk and shear moduli. And if you calculate everything, you will explicitly get a velocity correlation function out of this, a mesoscopic correlation function with the length scales in here. So one for the longitudinal and one for the transverse, which is actually very simple. So the time persistence here leads to a length scale. So longitudinal, for example, or say transverse here, square root of tau, persistence time, shear modulus, friction coefficient. So very simple. and going like the square root of the persistence time. So again, this goes away when the system is passive. So there's a very explicit reason for why you see this mesoscopic correlation length. So there's a linear response calculation, and it's actually surprisingly rather generic. I should say we're not the only ones who came up with this. This has been sort of simultaneously discovered by 5 or 6 different people. Yeah. And this works very well, and it really explains where this stuff comes from. So you can see it, for example, here for active Brownian particles. This is for a very persistent system. You can see this is a velocity field which is very correlated, essentially system size correlated in here. And you can see the velocity correlation functions here. If it's almost thermal, it's very nearly flat. But then you acquire, essentially, the tail here drops and the front part drops less, and you get more and more of a scaling regions of the 1 over q square, where you can see the emergence of this correlation length. I should say normal modes are continuous here and work very well with the simulation. So this has been generalized further, and it's one of a type of an active turbulence. So there are many other types, including from active pneumatics, which we won't have time to talk about, but this fits within these approaches, including extensions to systems which are more liquid more recently. So this is generic. These come explicitly from the active driving coupling to persistence. I'm going slow, right? So I wanted to come back to something which was mentioned briefly, which was a paper of Rika Aller and company, Turning Away. So I wanted to say one more thing about solids, essentially, which has active driving, is that you can, in fact, instead of just doing active Brownian motion or flocking, as we've done already, you can do something much more interesting. So there is another type of this type of active driving which is interesting, has recently gotten a revival, which is force alignment or self-alignment. So the idea here is that I use the same equation of motion as for active Brownian particles. So my force has self-propulsion and pair forces, but my director here, instead of just having noise, like here, this is a 3-dimensional version of ABP, it also has this particular coupling here. Let me explain what this is. It's written in a pretty complicated way, but the idea is simple. It says my director N is going to have dynamics which couples it to the velocity or the total force on myself in such a way that it will try to align with the direction I'm being pushed. So it's very generic, and you can show this shows up for mechanical systems systematically, that if I'm being pushed somewhere and I'm polar in any way, for example, unbalanced or actually elongated, I will slowly reorient myself with the direction I'm being pushed. And this equation here encapsulates that particular coupling. Now this has some very interesting consequences, and it has been theorized, say, for cells multiple times as well, is if I stick this stuff into confinement, it will oscillate. And if I stick this thing outside of confinement, so I should say, I'll show this in a moment, this is cells, it will self-propel. So the self-propelled version of this was first introduced by people on Szabo, so this is known as an alternative flocking model. But the fact that this thing oscillates is really interesting. It has popped up over the years several times, including I did this a long time ago for a system like this, and has been recently looked at by Paul Baconnier and Olivier Dauchot as the actuating oscillating system. So this is a generic way of getting some very interesting local active elastic dynamics. And there's a recent review article on this topic. Any questions here? Then with what time I have, and I'm going to probably abbreviate it a bit, I want to tell you a little bit about cells and how to model them. So you saw a bit of this in the intro already, but I will show you again. So what you're looking at here is cell sheets on the substrate, and you can see they make this correlated fluctuating, spatially heterogeneous motion. And I wanted to say here, by the way, that the model which I just showed you for the velocity correlations, yes, actually applies to this. This makes a good quantitative model of this kind of motion, ABPs actually. I should say at the same time, cells are more complicated, and there's a lot more things going on, like they're elongated, squishable, they have active stresses between them, so there is a large community which interprets these as active pneumatics with topological defects, and I'll come back to this if I get time. So I wanted to say, though, since I think this audience is a bit different, I want to tell you what are we actually looking at. If I say epithelial cell sheet, what should I imagine? So I should imagine something which looks a bit like a cobblestone pavement with an cytoskeleton, actomyosin filaments, mostly concentrated here at the top. And here is a nice stained MDCK monolayer where you can see in green the actin cytoskeleton, the blue the nuclei, and here in red this is individual dividing cells. You get a system which is both pulling on each other, moving over substrate if it's there, and dividing. And so you'll talk about pulsating in a bit later, yeah? This can have different incarnation. So if I want to model something like this as an active material, I need to take into account at least two different kinds of activity. So I should say, well, I'm going to pretend this is like squishy blobs, but they can be active in two different ways. So they can either be crawling over substrate because of the net force from like pulling over it, think of a slug crawling or in your garden, or they can pull on each other. So cell-cell active stresses of actomyosin, and this is what I call type 3 in my overview slide on active solids. This one here would be type, I believe actually 2, sorry for that, yeah, crawling. And I'll show you, and then you can model these in different ways. So this one here, essentially, I showed you already self-propulsion, ABP cell driving is okay with this. I'll tell you a little bit about vertex models in a moment. This is the frontier of the field currently, is how can I model these things when things pull on each other and I don't want to do it in continuum, I want to do it microscopically. This is where there is a lot of movement in addition to the continuum active pneumatics, which is a separate area. So I wanted to tell you two things. So first of all, I need to make a good model for my squishy cells. So soft particles are not bad, but they're not great. Instead, what people look at, and here is something like this. So if I look at a cell sheet from above, as I said, this is like a cobblestone pavement, and one thing in particular is that this thing is what's called confluent. There are no holes in between there. This is always dense, and in fact here a monolayer. And then I look at this and squint a bit, like physicists about 15 years ago, they say, well, I've seen this sort of thing before. It's called a foam, yeah? It's called, in fact, in particular, what's called a dry foam. So a foam where the liquid between the edges has drained out, and it makes nice polygonal or more or less polyhedral shapes in there. So people took this as inspiration and said, let me take the physics of foams or the numerical approaches to foams and try to make a model out of this for things like cell sheets. And born out of this, what's become known as the vertex models. So first Nagai and Honda, then this is Faraday, Farhan-Ehrlicher, and then lots and lots of people since, yes. And so the idea is I'm going to, in 2 dimensions, pretend this is a polygonal tiling with nice straight edges mostly. And so the idea is every cell is a polygon with an area A, a parameter P, and then I'm going to borrow from foam physics and say I'm just going to pretend that there's an energy functional in there and then hope for the best as a first step, yeah? So I'll construct an energy functional. And so what's become now the consensus version of this in the physics community is the following one, which says it has 2 terms. It has an A minus A0 square, where A0 is the target area, so I'm going to punish fluctuations of my area away from a target area, so it's a compressibility bulk modulus kind of term. I'm also going to punish fluctuations of my perimeter from its target parameter, and that's a combination of like active pulling forces, adhesion, and many different other things which you can recast in this form. So parameter change penalty P minus P0 square. So originally people just minimized this using something like surface evolver, which was done for foams, but clearly when I talk about active materials, and as you've seen the movies before, this is insufficient. So how do you make this active? And so the simplest way to make this active, consistent which I told you about crawling, is in fact to say, let me close my eyes and I'm just still going to take my cell to be a polygon driven at the center, and let me just put my motility at the center and then say, okay, let me drive this just like active Brownian particles, but with interactions which are the gradients of the vertex model potential, so which are much more complicated, but essentially active Brownian driving with self-propulsion and rotational diffusion of the angle, but with the gradients of the vertex model. Sorry. So I should say this is actually numerically not simple. The reason being is that this only works if the cell centers are the points on Delaunay triangles, and the cell shapes are Voronoi tiles. So you need a continuous differential map between these things back and forth for this to actually work, which is why this has become known as the self-propelled Voronoi model here, the SPV. So let me show you what you're looking at here. So in particular, something these models inherit from foam models is something called a T1 transition. So that's a transition where cells exchange neighbors. So let me play it once more. Right, here we go. Follow this edge here. It's shrinking. Then it's rearranging. And this is the exact same point where you change, where you actually flip these pair of Delaunay triangles to the opposite. So this is the geometry, planar graphs, important for this system. So this model was introduced by Max B, Lisa Manning, and co-workers. And it is very interesting because this model, in fact, has a rigidity transition. So this model has a transition which looks a bit like a glass transition picture. And in one direction, in fact, is V0, the active driving as expected. But on the x-axis is something different. On the x-axis is what is now known as the shape parameter P0, which is square root of the target parameter divided by the square root of the target parameter divided by the square root of the target area. This dimensionless. And this number, for example, if it's 3.72, that's exactly a regular hexagon. 4 would be a square. 3.81 is a regular pentagon. And what you find is that even without driving, there's a transition between something which is solid and something which is fluid. In this case, defined as being rearranging, under an infinitesimal driving. Pretty close to 3.81 and very slightly dependent on the details of the active driving. But so this is an example of something like a solid, liquid solid or glass-like transition in a system which is not a standard glass former, and density is irrelevant here. These are all confluent tissues. These all have packing fraction effectively 1 because there are no holes in between here. Here's an example. This is one of our codes, and you can see this is a liquid phase sort of somewhere around here. So starting with the P0, which is lower, but then driven into the liquid phase by activity. So as you can see, it makes actually a pretty good looking type of tissue. I wanted to very briefly tell you about going further than that. So to go further than that, you would have cells which can pull on each other, and so they explain things like these perceived active pneumatic properties or hexatic properties like my colleague Luca Giomi is investigating. And essentially in a nutshell, we think these all arise from cells producing stresses which are like this, one pulling on each other, for example, along their junctions. Now this is complicated. And nonetheless, because you actually need to start looking at biology, and you can say these come, I need to understand how junctions work. So these pull on the substrate, these pull on in each other. They need to be such that they, in this case, follow action-reaction if I have them pulling on each other. So these are not non-reciprocal. These are reciprocal forces always. And essentially, you need to marry vertex models with mechanochemical feedback and similar of things pulling on each other. And very briefly, we'll give you an example. So for example, one of the processes we're interested in is something called, I showed you earlier on, is gastrulation. So you can see things folding inside out here. And there's a process here exactly around here, which is called germ band elongation, where this goes wider. And if you follow these cells in the germ band, you will see that they flow sideways, but that they're elongated up-down. So this is a very strange active process. I can tell you more about this if you're interested. Where things are under stress or polarized up-down, but they flow left-right, which can be mapped to something with a negative shear modulus, which should be illegal. in equilibrium systems. So you can see it's polarized up down, but the flow is in the opposite direction. So for example, for stuff like this, and don't want to do details, you need to make individual junction models which have actomyosin on them, which have feedback in them, which react to stress. So you need to really go into the molecular details of these things and try to come up with general principles. In this case here, a catch-point principle of why this is happening. Then ask me about details if you're interested. You need to be careful and do your simulations right. So you need to stick your simulations on a proper mesh, no self-propelled Voronoi, no nothing. You need to really take these junctions as serious mechanical objects. So you need to make a mesh simulation. And this is, okay, my colleague Rasmus Knepnig I work with is actually pioneer of this sort of thing. You need to find a way of transversing things in your mesh. So there's a very nice literature which has been borrowed from people doing things like 3D games and similar, which is called a half-edge procedure, where you can, as long as your mesh is planar, meaning non-intersecting and two-dimensional, you can go from anywhere to anywhere through a method called half-edge, where you go around, go opposite, and you can navigate everything this way. So you can write this in C++, map and combine this with Python, and this is the way to make an actually nice and fast vertex model code. So once you have stuff like this, you need to write down equations of motion. So I've done this for you here, still over damped dynamics with tension. So for example, for every vertex, you have a tension along each of the junctions, the directions of the junctions, and you have forces which come from the areas. So this is a long annoying calculation, but these tensions are given by pieces here, gamma p minus p0, which come from the vertex model, but there should be an active term here. There should be explicit active tension. Similarly, these area forces are inward, coming from the area terms, kappa A minus A0, but they could have active components in them as well. So I should say both these terms come from the gradients of the vertex model. Now, there's a whole zoo of these, which is underexplored. Just wanted to showcase, if you do this, you can do stuff like this. So there's an active inclusion in a passive system. This is for these germ band-like systems. I pull this. Give me a second. I polarize it. Sorry, that went too fast. 1 second. So I've pulled the system now. It's under stress left, right. I have actomyosin concentrated on these junctions and tension as well. Then I make this thing active and let it evolve. And I will eventually be able to rearrange backwards. So it pulls back around, come on, here. Yeah, it pulls back against the applied stress and rearranges against the stress applied to it. So this is a negative strain increment. If you know elastoplastic models, this is like a backwards Eshelby deformation. And you can in fact make models based on these systems. We're working on that currently. But this is an example of the sort of thing biology can do, which is weird in a soft matter kind of sense. And with that, I'm actually done here. Just outlook, the future for tissue models is if you want to really talk to biologists, there's two things. You need to do this properly in 3 dimensions in a computationally sane way, which is currently not obvious at all. And you want to work on very cool new systems like organoids, where you make little, almost organ-like systems in the lab, which you can treat exactly like you want with different labels and similar. But also caveat emptor. This is my favorite XKCD, yes. So it says, please read it. So you're trying to predict the system of the behavior of complicated system, just model it as simple objects and then add some secondary terms to account for complications I just thought of. Easy, right? So why do you need a full journal for your field? So this is your typical physicist trying to talk to biologists, yes. This does tend to not end well, yes. So if you want to work with biology people, you really need to listen what they have to say. This is not easy. And I remember with one of our collaborators, we spent, I think, a whole year just communicating in videos because they have their own language using genetics and similar, and it's just half the time you spend first translating one into the other. But when it works, it works very well. And so I wanted to hand over again.